Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Welcome back. We'll switch gears a little bit from the linear motion that we have been studying so far and see how we can study rotational motion. It's not that different from doing the linear mechanics analysis, so if you paid attention at all, this shouldn't cause you too much trouble. So let's start from the geometric identity between linear motion and rotational motion. So here we have a point that's rotated through an angle theta. In that time it has covered the length of an arc that we call S, and this is the radius. And the angle theta, that is expressed in radians from now on, is the length of the arc S divided by a radius r. And if it takes time delta t to go through this angular displacement, then we can define the angular velocity. So the average angular velocity from going from here to here, that would be just a change in delta theta divided by change in time delta t. As you can know, or as you've seen before, so then we get the instantaneous angular velocity if we take the limit when the delta t goes to 0, and we have just simply the time derivative of angular displacement with respect to time. And let's add one more subindex here. So we usually, or for example, we can call it omega average z, and z means that it is the axis of rotation of this motion. So in this case, the z-axis would be pointing out from the screen like this, and you'll see in a minute why we do this. In a similar fashion, we can say that the angular acceleration average about axis z is change in the angular velocity divided by delta t, and hence the angular acceleration about axis z would be change in the delta omega with respect to time, or this is of course the second derivative of the angular displacement. And we can continue the analogy from here. So in addition to saying that theta is s divided by r, we can say that the angular velocity can be related to the linear velocity in the same way. So for example, at this point here, it has some tangential velocity v, then the angular velocity is v divided by r. And also if it has some, or the angular acceleration would be the linear acceleration, if it had any, divided by r. The fact that the angular velocity is time derivative of angular displacement and the angular acceleration is the second derivative of angular displacement, that leads to almost the same equations for rotational motion under constant acceleration as we had for linear motion under constant acceleration. So let's have a look at these formulas. Here on the left hand side we have the stuff that we learned earlier for linear motion, and as you can see, when we are operating in the angular realm, the equations are almost the same, except for that the displacement that on the left is called x, that has been replaced by theta. Velocity v has been replaced by angular velocity omega, and acceleration a has been displaced by or replaced by angular acceleration alpha. So applying these equations should be pretty straightforward if you were familiar with them in the linear world as well. As you are aware, velocity and acceleration and also displacement were vector quantities in the linear world, and so are angular velocity and angular acceleration as well. And how does this concept translate to something that goes around a central point, for example? Here is the right-hand rule that will pop up in physics in various locations. And the way this works is that first we have to determine the direction of the rotation, or the velocity or acceleration, whatever we are evaluating. And then we curl our right-hand fingers along the directions. And our thumb then will point to the direction of the rotation axis. And that is the direction of the angular velocity vector, for example. So, for example, the magnitude would be, let's say, 10 radians per second. And for curiosity, let's look at the example here on the right. So in this case, let's make this axis. So we have z-axis pointing up. Same thing here. And now that our thumb is pointing down, this means that the z component of the angular velocity is negative. So hence we have the w or omega z minus 10 radians per second. And then the angular velocity vector would be minus 10 radians per second in the negative z direction. So we have negative, and z direction is noted by the unit vector k. And in this case on the left, the omega would be, or the omega vector would be 10 radians per second, and in the positive z direction, so hence positive k. This is identical to the definition that, let's say, we have positive x direction that way, and then we have particle that is moving to the left with the velocity v. The speed v, let's say that would be 10 meters per second. The x component of the velocity would be minus 10 meters per second. And then finally the v vector itself, that would be minus 10 meters per second to the negative x direction, hence minus I. So the analogy is definitely there. You just have to make sure you get the sign right by curling your fingers according to the direction of the motion and looking which way does your thumb point. We have one more topic to cover in this presentation, and that is how do we deal with acceleration in a rotational motion. We saw a part of it, but let's not forget the piece that we already learned, and that is the fact that when there is a circular motion, there is also always the radial acceleration. And let's refresh our memory to see what I mean by that. Here is a particle on a circular path going at the velocity v at this very instant. And here we have the radius of the motion, or the radius of the curvature. And in such a case, there is always the radial acceleration component, because the direction of that velocity vector is changing, and the magnitude of that was tangential velocity v squared divided by r. And what can we do with this v? So if you look from here, so let's keep these definitions in mind. In that case, v is just omega times r. So we get omega times r squared divided by r, and those cancel, so we have omega squared divided by r. That is the magnitude of the radial acceleration when the angular velocity is omega. And of course, if this particle would be speeding up along this trajectory, so the magnitude of the v would be increasing, then it would of course have tangential acceleration. We call it a tangent. And this is in fact what is meant by this a here. So this is a tangential, and this is of course v tangential as shown here. So the tangential acceleration is the angular acceleration times r. So for acceleration now we have two components. First of all, we have the radial going this way, and then possibly if the particle's velocity or speed is changing, it has tangential acceleration. And here we have the a radial. So the total acceleration of this object is the vector sum of the two. So let's say this reaches all the way here. So we have the tangential component and the radial component. Hence, the total acceleration would be the vector sum of the two, like this. So that's the total acceleration in this case. We can then, of course, calculate the magnitude of the total acceleration, and that is just the square root of the Pythagorean sum. So a radial squared plus a tangential squared, and the general expression then becomes, oh, there's a mistake, by the way. Of course, the r has to be there because those cancel. So omega 4th power r squared plus the tangential component squared, like this. And we can also, if needed, calculate the direction of the acceleration from these components. Hence, when going through a rotational motion, if you think about yourself in a theme park ride, for example, you don't only feel the squeeze from the side, from the radial acceleration. There might also be push from behind or from the front, depending if the rate of the rotation is increasing or decreasing. And that is exactly what angular acceleration is about. So you have to be careful not to forget this one, or check its existence in any particular case.